So the first paper of the session will be Temporally Stable Real-Time Joint Neural Denoising and Supersampling. The authors are Manu, Mathew, Thomas from UC Santa Cruz, Gabor, Liktor from Intel, Karthik, Vaidyanathan from Intel, SungYe Kim from Intel, Christoph from Intel, and Angus Forbes from UC Santa Cruz. Manu will be giving the talk and will be here after to answer questions.
Hello, my name is Manu Mathew Thomas, and I will be presenting our paper titled Temporally Stable Real-Time Joint Neural Denoising and Supersampling. This is a work from Intel Graphics Research with Gabor, Liktor, Christoph, SungYe Kim, Karthik, Vaidyanathan, and Angus Forbes. The goal of our work is to improve image quality and performance of ray tracing in games. This is achieved by introducing a novel neural technique that combines supersampling and denoising. In the teaser shown here, on the left, we have a low-resolution composited input signal that is undersampled to meet real-time budget, producing noise and aliasing artifacts. On the right, we show the results from our joint approach, producing a high-resolution output image that is denoised and supersampled. Ray tracing is now widely used in games to create realistic light effects such as soft shadows, glossy reflections, and diffuse global illumination. We are still limited to a few rays per pixel for achieving real-time performance, resulting in noisy images. To reconstruct a noise-free image, we rely on spatiotemporal filters such as the analytical Unreal Engine denoiser or the statistical-based spatiotemporal variance-guided filters. Even with limited use of ray tracing effects, rendering and denoising at display resolution is expensive. Instead, we can render and denoise at a lower resolution and make use of advanced upsampling techniques to get performance gains. Recently, neural supersampling techniques such as Intel XeSS and NVIDIA DLSS are gaining huge popularity and have been successfully integrated into many games due to its ability to produce high-quality results compared to the traditional techniques. Neural denoisers produce high-quality results compared to handcrafted filters, but are not used in games due to the higher cost associated with these networks. They have become standard reconstruction techniques for offline and interactive rendering, and it's still an active area of research improving quality and performance. Designing a neural denoiser for games can be challenging because we want both real-time performance and good reconstruction quality. If we use neural denoiser at the native resolution, we would get a high reconstruction quality, but with high computational cost. We could use a neural upscaler with the neural denoiser. This would reduce the shading cost, and we would get a high reconstruction quality, but chaining two neural reconstruction techniques can be very expensive and not practical in most scenarios. Our approach is to combine denoising and supersampling into a single network that produces temporally stable, high-quality reconstruction in real time. Our network takes low-resolution input, which is noisy and aliased, and reconstructs it to a high-resolution denoised supersampled output. The first step in designing our neural denoiser is to look at the available image reconstruction networks. Chaitanya et al. Introduced the recurrent unit-based direct prediction network for interactive denoising. The advantage of unit is that it can achieve large receptive field with low cost. The downside of direct prediction is that it tends to produce ringing and color shift artifacts. Paco et al. Proposed kernel prediction networks, where the output of the network is a per pixel kernel, which is then applied to the noisy signals. Kernel predictors overcome the problem of direct prediction networks, but predicting and applying a single large kernel increases the complexity and not real-time friendly. Asselgren et al. And our previous work on quantized supersampling network explored combining unit with kernel prediction. Here we predict hierarchical kernels that achieve large spatial footprint with lower cost compared to predicting a single large kernel. This network is a good candidate for real-time inference. We use this network as our base design. Our unit feature extractor produces a shareable feature representation that is then used by the kernel predictor to generate filter weights for multiple reconstruction tasks. The shareable representation avoids the need of running separate units for each reconstruction. The noisy signal is decomposed into its different components so that the kernel predictor can generate filters designed for different noise characteristics. We have specular and diffuse, which are noisy, and we demodulate albedo from the diffuse to support aggressive filtering without blurring the texture details. The albedo is noise-free but has aliasing artifacts. We also use normal and roughness as auxiliary buffers to guide the network. Additionally, we use previous warped result to help with temporal accumulation. Providing all these buffers as input to the feature extractor directly can be expensive since the first two convolution layers in the encoder and the last two convolution in the decoder stage must operate in the native resolution. Instead, we add a lightweight input and output block to extract features from native resolution and use the unit feature extractor in a subnative resolution, reducing the number of per pixel multiply accumulate operations. For filtering diffuse and specular, we predict hierarchical filters resembling the shape of a unit, but there are no learnable parameters associated with the filter paths. The input to the specular filter path is the noisy signal and the warped previous result. The output is the denoised specular. Diffuse filtering is similar to specular except we predict a different set of filter weights. For aliased signals, a large receptive field is not required, so we only predict filter weights for native resolution. The input is the albedo containing jagged edges and warped previous result. The output is the supersampled albedo with smoother edges. The supersampled normal is only used as a guide for the feature extractor. Once we get the results from the filtering paths, we can do a composite to get denoised and supersampled result at the native resolution. We use a simple compositor where the supersampled albedo is modulated with the denoised diffuse, and then add it to the denoised specular. The final component is the upsample block. Here we reuse the features from the feature extractor to predict kernels to filter at target resolution. The input is the denoised supersampled composite, and the output is the upsampled result. Here are some examples to demonstrate the effectiveness of our upsample block. We show composited results before and after the upsample block along with the corresponding reference images. Our upsampling results show sharper details on texture and fine geometry that are comparable to the reference in the target resolution. Here is the complete network architecture with a single feature extractor and multiple filtering paths. To further reduce the cost of running this network, we quantize all the non-filtering blocks to int8 precision without any significant loss in image quality. To perform training, we generate all the dataset using a modified version of Unreal Engine 4. We captured several sequences with different camera paths from 6 cinematic scenes, and each sequence is labeled as train or test. The reference images are captured using 256 jitters per pixel. For shadows, we use 16 to 32 rays per pixel per jitter per light, and for reflections and diffuse GI, we use 64 to 128 rays per pixel per jitter. The network is trained in full precision mode initially, then it is retrained as a fine-tuning step with the quantized weights and activation. We use per channel symmetric quantizer for weights and per layer affine quantizer for activations. The choice of the loss function is very important to get good results. We found L1 loss to produce significant blur and loss of details with undersampled inputs. Perceptual loss functions used in image super-resolution networks tend to produce sharper results. The features from VGG classification networks, which is trained on natural images, are used to define the perceptual loss. When used with our network, we observed pattern artifacts in high noisy regions. To overcome this issue, we trained a loss network on publicly available rendered images and used the features of this network to define our loss function. Our custom feature loss reduces the pattern artifacts significantly. Okay, now let's look at some results. Comparison to state-of-the-art denoisers at the target resolution reveals that our method, although receives 4 times fewer samples, is able to reconstruct image features more faithfully and achieve good sharpness. The PSNR metric is shown on top row and SSIM shown in the bottom row. When we compare with denoisers running at native resolution, we consistently see better reconstruction with our technique, while also producing a higher resolution output. To compare with neural upsampling techniques, we apply XESS to Unreal Engine 4 denoiser results. XESS brings a lot of image details compared to traditional TAA techniques, but our network outperforms at reconstructing high-frequency details as shown in the top row. Here is the video comparing all techniques to demonstrate the reconstruction quality in an animated sequence. Compared to other denoisers, our method produces temporally stable results without significant flickering or ghosting. In this close-up, we see disocclusion, and our method recovers immediately while the competing denoisers struggle to reconstruct. The character's hand moves across the scene covering the plant. As the hand moves away, the plant is disoccluded and there is not enough information to recover. UE4 denoiser plus TAA fails to reconstruct, leaving residual noise. Our network learns to predict spatial filter weights that blurs this region, providing better reconstruction when the history samples are unavailable. Like other denoisers, our technique also struggles with reconstructing specular highlights that are undersampled. In this example, we see our network reconstruct most of the scene details but fails in the specular regions. Another limitation of our method is the reconstruction of initial frames. Since we rely on temporal accumulation, we see some noise in first few frames, but recovers quickly as we start accumulating samples. After about 5 frames, we start to see good reconstructed results. To compare performance, we use an RTX 3070 to measure timing for all the techniques. For SVGF and UV4 denoiser, the input and target resolution is 1440p, while our network takes 720p input and produces a 1440p output. For the spaceship scene, we see that our technique has better timing than Unreal Engine 4 denoiser, but slightly expensive than SVGF. The real benefit of our technique can be seen when we add the shading cost. Since we use low resolution input, our shading cost is also significantly lower. This trend can be seen in other scenes as well. The overall cost of rendering a frame is significantly reduced without compromising the image quality. To conclude, real-time neural denoisers for games are within our reach. We show our joint denoising and supersampling solution, where one feature extractor is shared for multiple filtering tasks. Our method can provide high reconstruction quality at a lower cost. Thank you.
Thanks for the presentation, Manu. Very impressive work. We already have 2 questions on the question board, but 3 now. Don't hesitate to actually put yourself in question list. So I will start with the first two questions, which are kind of related, and they are regarding the loss you use. So you add an extra term to the loss to actually improve the quality, and for that you use kind of a custom, your custom BGG, your feature loss kind of. And the first question was, why not use a gab for that part? Because it could also improve sharpness. And the other question by Bart Vronsky is, how is it different from PGG/LPPS loss, which are both trained on like internet datasets?
Right. So yeah, so we have tried some experiments initially with GANs, but the trainings were not very stable. So yeah, we still want to pursue GAN, and it's still a future work for us. One challenge that we have is that we have several filter paths, and for each filter path we use a separate loss function. So adding a GAN would increase the training time as well. And for the second question, yes, so yeah, our feature loss is similar to VGG, but VGG is trained on natural images to for classification problems, and there are several works that shows that VGGs are sensitive to textures. So even if you don't show the object and you just show the texture, it can differentiate. So there's a texture bias, and we kind of avoid that by training with a rendered data set, and the objective of our loss function network is semantic segmentation.
I see. I was curious also because it really adds something. And were you planning to release this particular feature extractor?
No current plans to release.
No current plans. Thank you. So there's another question from Andrew. Can you describe your GP implementation and any optimization there?
Right. So yeah, for GPU implementation, we used TensorRT for all the network components. And TensorRT does a lot of optimization inside, but it's not complete yet. We could go even further with custom implementation, like fusing layers together, and we can improve the performance. And